This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 1 of Week 4, Pump Head and Hydraulic Power. We turn pressure, velocity, and elevation into one length called head, the universal currency of every pump problem. Then convert head and flow into power in SI and US units. Pumps are rated in head, a length, not pressure. Head is energy per unit weight of fluid, so it normalizes away density. The same 120 feet of head gives a different pressure rise depending on the fluid, about 52 psi for water, only about 37 for lighter gasoline. That's why a manufacturer publishes a head versus flow curve, not a pressure curve. One curve covers every fluid. Convert to pressure only at the end, using the fluid's specific weight. It's the same head term from the extended Bernoulli equation in Week 2. Total dynamic head. The pump head from suction point 1 to discharge point 2 is the rise in total energy per unit weight, and it splits into three length terms. Pressure head, the static pressure rise over rho g. Velocity head, the change in kinetic energy per unit weight. Elevation head, the literal lift, Z2 minus Z1. Add all three, and you get the total dynamic head, or TDH, the universal currency every pump problem reduces to. A shortcut: when suction and discharge pipes share a diameter, the velocity head term vanishes. But write all three first, then cross out what's zero. The variable table for every pump power problem. Flow rate Q, cubic meters per second or GPM. Total dynamic head, H, meters or feet. Fluid density, rho. Specific weight, gamma, which is rho g. Specific gravity, a pure ratio. And the answer, hydraulic power, watts or horsepower. The only constants you bring are gravity and the fluid properties. Gamma equals rho g ties the two property rows together, and for any non-water fluid, you scale the water value by specific gravity. Hydraulic power. Once you have head and flow, the power delivered to the fluid is just specific weight times flow times head, rho g QH, or gamma QH. They're identical. In consistent SI units, it lands straight in watts, no conversion factor. One caution: this is hydraulic power, the useful energy added to the fluid. It's always less than the shaft power the motor must supply. That efficiency gap is the next topic. Same physics, US clothing. Flow usually arrives in GPM and head in feet, so the handbook packages every unit conversion into one constant, 3,960. Power in horsepower equals flow times head times specific gravity all over that constant. It bundles three conversions for water: gallons per minute to cubic feet per second, water specific weight, and foot-pounds per second to horsepower. Here's the trap baked inside. Because water's specific weight is already in the constant, you must multiply by specific gravity for any non-water fluid. For water, it's 1 and vanishes, which is exactly how people forget it's there. Place hydraulic power in the bigger picture. It's what the fluid actually receives. Walk back upstream, and each stage adds a loss. Shaft power or brake power is hydraulic power divided by the pump efficiency. Electrical input is hydraulic power divided by both the pump and motor efficiencies. Today we nail down only the first link, gamma QH. One sanity rule: hydraulic power is the smallest in the chain. Shaft power bigger, motor input biggest. If your shaft power ever comes out smaller than hydraulic power, you divided upside down. Worked problem. A centrifugal pump moves a light oil, specific gravity 0.9. The duty point, 500 GPM, 120 feet of head. Find the hydraulic power delivered, first in horsepower, then in kilowatts. The plan: use the US shortcut, then convert horsepower to kilowatts. Then cross-check from the SI form, rho g QH. Plug the duty point into the handbook constant, 500 times 120 times 0.9 over 3,960. And you get about 13.6 horsepower, which is about 10.2 kilowatts. Notice the specific gravity pulled the answer down 10% versus water. Forget it, and you'd overstate the power. Mind sig figs. Report 13.6 horsepower, 10.2 kilowatts. Now, The SI cross-check. Convert each quantity to SI, then apply ρ g to H. The oil density is 900 kilograms per cubic meter. Multiply through, and you get about 10.2 kilowatts, the same answer. When two independent unit systems agree, your unit handling is sound. 4 traps. 1. Head versus pressure. Head is a length, pressure is force over area, linked by delta P equals gamma H, but not interchangeable. 2. Forgetting specific gravity for non-water fluids. The constant has water baked in, so multiply by specific gravity or your power is off by that ratio. 3. Treating 3960 as dimensionless. Use it only with flow in GPM and head in feet. 4. Mixing unit systems. The gamma QH form needs all SI or all US inputs. Convert first, then multiply. Bookmark the pump pages. The total dynamic head definition. The three-term sum of pressure, velocity, and elevation head. Hydraulic power in SI, gamma QH straight to watts. The US shortcut with the 3960 constant. The power chain to shaft and motor power. And the root of it all from Bernoulli. Head is energy per unit weight. The head definition and the shortcut are the two you'll reach for on almost every pump problem. You now own the first link, gamma QH, the useful power delivered to the fluid. In topic 2, we walk upstream, divide by pump efficiency for shaft power, then by motor efficiency for the electrical draw. Same duty point, we just account for where the energy leaks. Bring today's 10.2 kilowatt number. It's the numerator of every efficiency calculation next time. See you in topic 2.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.